Okay, so hello everyone. Uh, I think we'll wait for some like 5 minutes. Then we'll start the live session so that some more students can join the live session. So just wait for 5 minutes. Then we will be starting. Okay. So yeah. Okay, so let me start this session. So let me first introduce myself. My name is Himanshi Singh. I'm currently pursuing PhD from the Department of Mathematics, IIT Jodhpur, in of probability and statistics. And I'm your TA for the course Essentials of Data Science with the R software 2, Sampling Theory and Linear Regression Analysis. Okay, and this course has been taught by Professor Shalab on the SYM portal, and they are uploading the content of every week there. And I'm just taking the live session at the end of the like in on every Monday to discuss the content which has been already shared and discussed with you in the previous week. So this is our ninth live session where we will be discussing the content which has been already discussed in week 9 lectures, and we will be considering some of the practical examples. We will consider some of the R codes or the demonstration in R, so that so that you can have a better understanding about the topic. Okay. And further, this is the live session schedule. So we have already completed 8 live sessions, and today it is our ninth live session. And apart from today, we have three more live sessions on 30th March, 6th April, and 13th April. Okay, so on 13th April, most probably it will be our last live session. Okay. Apart from this, these are the important links. So the first one is the Google Meet link, where by which you can join this class. The second one is the YouTube link, on which I am. So this is the link of my channel on YouTube, and here I am uploading all the recordings of these live sessions. Okay, so you can access it from there. And the third one is the Google Drive link, where I am uploading all my slides, the art scripts, and the PowerPoint presentations, which I am discussed here in this live session. Okay, so you may access it from this Google Drive. Fine. Okay, so these things are clear. Then, so basically, in every live session, what we are doing. So, if in the previous week, for example, this is ninth live session. So, if ninth week, whatever the content has been shared, I will be giving you a brief recap about it. Okay, and if there is something, then we will demonstrate that in R also. We will be doing some of the practice examples also. Okay, and apart from this, if anyone of you have some doubt, then you may ask, we can discuss on that also. Okay. So finally, so this is basically the structure for this live session. So we will start with the content. So in the previous lectures, we were majorly talking about about the sampling theory, basically. So where we have studied the simple random sampling, the stratified random sampling. We have studied the method of bootstrap estimation through bootstrapping, where also this random sampling and all those things are playing a role. Okay, so we have studied a little theoretical aspects of the thing, and also we have studied that how to implement those theoretical aspects in the R software. So how can we do those theoretical things using an R software in a more systematic, as well as in a more systematic way, of course, and also in so that the time consumption is very less. Okay, so we cannot do everything manually. So in order to for example, in order to reduce the time on computation by doing all the things on these things, this R software kind of thing is useful, and we are just implementing all the theoretical aspects which has been discussed regarding the sampling theory in R. Okay, so that was about the sampling theory. But from today, it's like now we are talking about the regression analysis, or more precisely, linear regression analysis. Okay, so here now, from now onwards, we will be talking about the regression analysis. Okay, and how to do that. So first we will study some of the theoretical aspects, and with that, so theoretical aspects, we will be seeing that how these theoretical aspects can be implemented in R. Okay, how can we do all those theoretical things by coding and get the results. Okay, so first of all, the main thing is model. So what basically model is? So for example, you have some so for example, you have a data set in like in a practical scenario. If I talk about, so if you have a data set, for example, water consumption of a person in a particular day. Okay, and the another variable is the temperature, what is the temperature outside. Okay, so so basically, so there are there are two variables, that what is the temperature outside, and the first variable, another variable is that what is the water consumption of a, for example, a household. And we are getting a data. So we know that through our intuitive understanding, that if the temperature is weather is hot, then water consumption compared to when the weather is cold. So as the temperature decreases, the water consumption will also be decreasing. That is kind of an intuitive thing. So apart from this also we can have a different kind of a data. So basically a relationship between variables. Okay, so this is kind of a relationship. So two variables, or I can say whatever a particular quantity we are measuring. So two quantities we are measuring, two quantities or two data considering, then two data may have some relationship. Okay, so and apart from this also, so one data may be dependent on other is independent, and one may be dependent on other. If in that scenario, so here I've constructed only two observations. Okay, so two on two things like water consumption and on temperature. Apart from this also I can have many more other things. Okay, apart from this also, if the weather is hot, the people who are going outside in a particular of a, so number of people if I calculate, then it may be less for the when the weather is hot, and it may be more when cold. So that kind of scenario, that kind of observations can also be taken. So we can have a multiple independent random variable which may constitute and give the value of the dependent variable. So basically there is a relationship between them. So let us consider, so we are here considering the let us consider x1, x2, xk random variables, okay, which are independent, which do not dependent on each other also, and which do not depends on another variable which is, and there is a relation between them. So basically if I change the value of the independent variable, the dependent variable is giving me a certain kind of a structure. So basically if I change the dependent variable way, then the independent variable in a particular way, then dependent variable will also be is getting changed. So the rate of change is having certain kind of a structure. Now that structure, it can, this relationship can be linear, it can be non-linear. So for example, if I consider in order to like have a pictorial view, so if this is a random variable, so this is a, sorry, observation x, here I'm considering, and here this is y. So when I'm increasing x, so if I have this kind of line, so basically what it is showing that as I'm increasing x, the y is also increasing. Okay, apart from this, if I have a line like this, so is that I'm increasing, y is decreasing. Okay, so this here I'm considering only line. Okay, apart from this line also, I can have some other kind of a relationship also, like of a relationship also. So this anything, this can be this also, this can be this also, whatever it can be, but there is some relationship. Okay, so this is basically, first of all, this assumption x2 xk are the observations or the variables which are independent, and y is a variable which is dependent on x by some function f. Okay, so this is in general a scenario. I don't know that whether f is a linear function or f is a non-linear function. So here, first of all, we will, so basically if I consider this, there may be there may be uh, 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 some more variables. Okay, so like beta 1, beta 2, beta k, that there are parameters which may in the behavior of y with this x1, x2, xk. So for example, if I consider this line, then y is equals to mx plus c, the equation of a line. So y is the variable, x is the independent variable, but this m and c are the parameters which, so basically y is equals to x. Okay, so basically independent and y is dependent variable, but this function of x, of what function of x? Okay, for example, if it is mx plus c, so there this function consists of some parameters. which basically is telling us about the relationship, that what relationship is, what is this relationship, and using the value of m and c, we can find out that what is the line. Okay, so that kind of parameters we are considering here. So this kind of function y is equals to f of x1, x2, xk, beta1, beta2, beta k plus epsilon. Now what this epsilon is? So basically is that there error. Okay, there may be some error. So for example, if I have a relationship like, so if I have a data like this, okay, then there may be this line which may fit to this data, because it is kind of a linear trend which may be explained by this line, but these not exactly lying on this line. Okay, but there is some kind of error, so that basically a random error. So the relationship may not be. So in a real life scenarios, these relationship cannot be exact. Okay, so that is a theoretical thing. You can only theoretically say that. So there may be some random error involved in the process, in the observations if we are talking about. Okay, so this a random error. So this basically, this phenomenon, this process, this relationship can be this behavior of the dependent and the independent variable can be explained by this method. Okay, now this relationship cannot always be exact. Why we are considering here addition of the random errors, so that there may be some kind of an error, a random error. Okay, so this is basically the we can say the format of considering the dependent and independent random variable. Now further we can talk about that, what about this function f? So how this function f, what that function f can be? Okay, so this that a function, if I consider in a broad sense, if I uh, between two uh, distinct, if I want to I can say, if I want to uh, partition a kind of a class of functions, then I can say a function can be linear, a function, so a function is linear or a function is non-linear. I can divide more better, where I can divide the population of a function can into two parts, that a function can be linear, a function can be non-linear. Okay, so here in the next slides we say, so basically this is a model, that is y is equals to f of x1, x2, xk. Okay, now the model here can be linear, it can be non-linear. Okay, so linear, non-linear means that we are talking about the function. So basically, so it can be linear, it can be non-linear. Now further here, linear and non-linearity, we are talking about this function. Now here we have x1, x2, xk are also there, beta1, beta2, beta k. So linear, if we talk about the regression analysis, okay, so we say that a particular regression analysis is linear if these parameters, that are beta1, beta2, beta k, if it is linear in these parameters. And we say that it is a non-linear regression analysis if it is non-linear in beta1, beta2, beta k. Okay, so there is also a scope that when x1, x2, when it is non-linear or linear in x1, x2, xk. But here in linear regression analysis or regression analysis, we are basically saying that it is linear in beta1, beta2, beta k. Then we say it is a linear regression analysis, and it is non-linear in beta1, beta2, beta k. Then we say it is a non-linear regression analysis. We are we do not have any effect on the regression analysis if it is whether it is linear in x1, x2, xk or non-linear in x1, x2, xk. We are not concerned with that. Actually, we only want that we will say it as a linear regression analysis if it is linear 1 beta 2 beta k, non-linear if it is non-linear in beta 1 beta 2 beta k. So basically that is only the thing. So here in linear, we the linear regression model is linear in parameters. So here in linearity also we can have other possibilities also when it is linear in for example x1, x2, xk. Okay, so that possibility here we are not considering. Same in non-linearity, we can have a possibility again. It is a non-linear in x1, x2, x3. We are not considering. We are only considering this linear regression model, basically a non-linear regression model, which says that it is linear in parameters and non-linear in parameters. Fine. Our main focus of concern is this linear regression model. Fine. So linear regression model means it is linear in parameters. Fine. So this is the thing. Okay. Apart from this, then if we talk about the linear regression model, okay, so then also we can have two classes. So whether it is a simple linear regression model or a multiple linear regression model. So in simple linear regression model, we are having one dependent variable, sorry, one independent variable. So the dependent variable is dependent on only one independent variable. Okay, so then we'll say that it is simple linear regression model. But if there are one independent random variable, then we'll say it is a multiple linear regression model. Fine. So this is a difference. So why we are, first of all, we'll consider simple linear regression model only because it is easy to get the visualization about the things. Okay, that how can we see the things actually. In when we go in the multi-dimension, then it may not be so it is not that easy to picturize. It is not that easy to imagine the things. Okay. However, when we talk about the simple linear regression model, so here we have only one dependent variable. So this is kind of a basically a line, okay, a straight line, a model kind like a straight line. So basically there is a data and we want to fit a straight line into it, a kind of a data which is showing a linear trend. Fine. So this is about this. So in today's class, we will be discussing about this model. Uh, for the multiple regression model, we will be talking about in the further lectures. Okay. So I hope my voice is clear. Okay. So fine. So see, simple linear regression model we are talking about. So here we call this beta naught and beta 1. So we call them as parameters of model. Okay. And they are called as the regression coefficients. Okay, so regression coefficients we basically call it, or we can call it as a parameters also, because further in the upcoming time we will be estimating them. So that's why this parameters this parameters notion is coming into picture. Okay, epsilon is what? Epsilon is the quantity because of which there is a possibility that the observation may not lie on the straight line. Okay, so basically we want this straight line. Okay, but the observation we took, so for example, if I so basically I don't know the process. Basically I do not know what is the straight line. I don't know how there is how the temperature and the consumption of the water, how they are related. I just know that okay, with the increase in temperature, there may be increase in consumption of the water, but I don't know that exactly what is the rate of that increase. Exactly what is the relationship? I don't know. Okay, now in order to know that the process is there, I know, but I don't know about that how exactly the fit for it. Okay, so for that what I will do, I will take a data. Okay, I will take observations like x1. I will take observation for this x, for example, x and y are the two things I want to check about the interrelationship. That I, for example, let's say y is equals to f of x. Okay, in fact, not f of x here, because we are talking about the linear thing. So this methodology basically is for all only. So y is equals to, for example, like this only, beta naught x plus beta 1 x plus beta 1 x. So I want to like I have some hunch that the relationship is maybe like this. Okay, but I don't know basically what the relationship is, exactly what it is, exactly what beta naught and what beta 1 are. So what I will do for the values of x, I will collect some data. Okay, I will collect, for example, n datas, x1, x2, xn, some values. For y also I collect some data, y1, y2. corresponding to this x1. So for example, for this temperature, what is the consumption? For this temperature, what is the consumption? For this temperature, what is the consumption? Okay. Now, if I collected this data, then for example, the pictorial view of this data is like, so here it is x, here it is y. So it is like this, for example. Okay. Now there is a linear trend that we can see from this data, that there is a linear trend in the data. Okay, that we can say approximately when we are increasing x, y is also increasing. Fine. So I want basically, but I don't know what exactly that linear trend is. So I want to fit a line into it, which will basically explain. So I want a fit to this data. So basically, I want to fit a line data. So this is the line. But if I'm fitting this data, so there in the observation and in the line, I have some difference. So for this particular value of x, I got y from the observation this, but on the line, if I see that the y is this, so there is some error. Okay, so now this error basically, so this is basically the, I'm taking it as an epsilon. Okay, so which accounts to the failure of the data to lie on the straight line. Okay, so this is the error, and also we will see afterwards that basically we will find the beta naught and beta 1 by minimizing these errors only. So this error is there for each observation. Okay, for some observation it is less, for some observation it is more. So we'll basically minimize, we want to basically minimize this kind of an error. Okay. Now, so basically the epsilon, the motivation for the epsilon is this only. Further, we want epsilon is IID random variable. Okay, and also the mean of this epsilon is 0, and and it has a constant variance. Fine. Now, further, further we want to estimate this beta naught and beta 1. So there are several methods, and two popular methods are method of least square estimation and maximum likelihood estimation. So these are the basic concepts of the statistical the point estimation in statistics. Okay, so this is least square estimation and maximum likelihood estimation. So in today's class, we will be considering this least square estimation. Fine. So further we move forward. So now we will consider that how to estimate this beta naught and beta 1. Fine. So now, for example, let's previously I have collected data pairs yi and xi for I1 to n. So let is y1 x1, y2 x2, y. Okay. And for each y, we may be making some error. Okay. So for each yi, in order to, so there is an observation of yi, and it may not lie on the straight line. It may lie apart from the straight line. So we are saying that epsilon I be the error which restricts this yi to lie on the line, this beta naught plus beta 1 xi. Fine. So this is the epsilon I. Further, this method of least square estimates what it do. It just wants to minimize the sum of the squares of epsilon I, the errors which we are making. So, or basically the errors which are present in order to fit a line into the data. So whatever the error is there, I want to minimize those errors. So that I want to minimize the square, the sum of the squares of those errors in order to estimate the beta naught and beta 1. So this is basically a method of least square estimate. There can be another method to find out beta naught, beta 1 also. But this method basically says that I want to minimize the sum of all the errors. Fine. So basically our objective is to minimize this quantity, summation of epsilon I square. Okay. So what basically epsilon I is? So our model was that yi is equals to beta naught plus beta 1 xi plus epsilon I. Okay, so this epsilon I is yi minus beta naught minus beta 1 xi. Okay, so I want to sum the square of this error. So I can find out the epsilon I. So it will be this square. Now you can see that this is basically a function of beta naught and beta 1. So I can minimize it with respect to beta naught and beta 1 in order to find out the beta naught and beta 1. Okay, so basically in order to find out estimates of beta naught and beta 1. Fine, on the basis of this sample, yi and xi's. So what we can do, we want to minimize it. So in order to minimize it, what we will do, we'll differentiate it with respect to beta naught, we will differentiate it with respect to beta 1, we'll equate it to find the values of beta naught 1 in the as a function of yi's and xi's. So by doing the whole process, it has also been discussed in the class that we got this estimates as beta naught had to be y x bar, where beta 1 hat is sxy divided by sxx, where sxy is this one. So we know xi, we know, so x bar is nothing but the mean. We know the xi's, we calculate, we observed this x1, x2, xn. So those xi's are there, their mean is there. We observed also y1, y2, yn is with us, so we know that, and we y bar also we know, so we can find out this quantity, we can find out this quantity. We the ratio, find out the beta 1 hat, and we will put that beta 1 hat here and find out the beta naught hat. Okay, so beta naught hat and beta 1 hat are found. Now we got this line beta naught hat plus beta 1 hat y, not y, x. Y is equals to plus x. Not plus x, is into x. Fine. So this will be our line which, okay. Now one more thing, like if I put the value of particular xi here and I found the yi, then there is a difference in that. So here we had this data, for example, we had this data and we fixed this line. So this line is basically this line. Okay, this line is this, for example, y is equals to beta naught hat. Okay, so if, so for example, this was our x. For this x, this was, so let me take it in a, for example, it is here. Okay, so for this particular x, I, we have this y on the line. Okay, this y on the line, but here this is the observation. So this is basically the, this is the observed. Okay, and this is the estimated, I can say. Okay, so there is a difference between them. So I can call it as yi hat, and this is, for example, yi. So this particular xi. So now this yi hat minus yi. So this difference, there is a difference. So this is called residual. Okay. So in the next slide, only this is there. So it is, sorry, it is yi minus yi hat. So this is yi minus, so difference we are talking about. So this is called as residual. So here you can say that we know that yi's are observed values of the dependent variable. Okay, values of yi hat can be calculated from the fitted model. So these are called as fitted values. Okay, and the quantity is this yi minus yi hat. So this is represented by ei. So it is called as ith residual. Fine. So this is about the how to find out the how to fit a line, a straight line into a data. Okay, how to fit a straight line to a data by using which method we are using? We are using the method of least square estimation in order to find out the coefficients, estimate of the coefficients in a more precise way. Fine. Now further, how we can do this all in R. Okay, so here, for example, let the data be dependent variable to be stored in a data vector y. So y is a dependent variable. I'm storing the data into a data vector y. I'm storing a data which is a data of independent variable into a data vector x. Then this command lmy and this tilde x. So this command basically is used to get the estimates of the parameter beta naught and beta 1. Okay, so this command is used to get those parameters. So here we have to do all this much of calculation, but by using only this command we can get the estimates. Okay, and if I want to find out these fitted values, that is bets. Okay, so these fitted values, so here which are lying on this line. Okay, I want to find out, then this can be we can find out using R by using this command fitted dot values lm y tilde x. So this will give us the fitted value yi hat beta naught hat plus beta 1 hat xi. So whatever xi's we have given, for all those we'll get fitted values of yi's. Okay. Apart from this, if I want to calculate these residuals, then I can calculate it using residuals, using this command residuals lm y tilde x. Okay, so these are the commands. So only these are the commands which can do all the work we have discussed theoretically. Okay, so I hope these things are clear. So this was the things which has been discussed in the lectures. Okay, now further we will start with the practice example. So if any one of you have any doubt, then you may ask. So if there is any doubt, anything regarding the concept, regarding the theoretical thing I have discussed, if there is anything, then you may ask. Otherwise, then we will move forward with the practice questions. Okay, so if there are no doubts, then we will start with the examples. Okay, so let me start with the examples now. Okay, so here in this question, it is asked, identify whether the following models are linear regression model or not. So linear regression model, so was the model where when the function or when the relation linear in the parameters. Okay, so one of the method to check that whether the particular relationship is linear in the parameter beta naught and beta 1 or not. So here we can see that the beta naught and beta 1 are the parameters, and x is the dependent variable. So one of the method is that just find out the partial derivative with respect to different parameters, and see that when you are finding out the partial derivatives, then whatever the derivative is of the parameter. Okay, so here we are having this beta naught and beta 1. So let us find out that the partial derivative of y with respect to beta naught. Okay, so that is what. So with respect to beta naught, it will be 1. Okay, with respect to beta naught, this will be 0. Because with respect to beta naught, it is constant, and it is also. So this is fine. So it is independent of the parameter. Again, dy over d beta 1. Not d, I should write del because I am considering to be a function of two, I can say a function of two variables. Okay. Over del beta 1, so it is sine of, which again is a independent of parameter. So both are independent of parameters. Hence, linear regression model. Hence, it is linear regression model. Further, let us consider other expressions. So this is y is equals to beta naught plus beta 1 x plus beta 2 x square plus epsilon. So again, take del y over del beta naught. So it will be and otherwise it is 0. So it is 1. Del y over del beta 1. So it is 0 here, x here, and 0 here. Other it is x, so it is not independent of the parameter. Del beta 2, so it is 0 here, 0 here, x square here, so it is x square. So again, all the three are independent of parameter, hence it is linear regression, because all the three are independent of beta naught, beta 1 and beta 2. Again, if we consider this y, then you can see that del y over del beta naught. So it is what? 1. Because it is 1 for this, 0 for this and 0 for this. So it is 1. Again del y over del beta 1. So it is what? So if I differentiate this, so it will become, so this is with respect to beta 1 is 0. If I differentiate with respect to beta 1, so it is 2 beta 1 x. And this is not, so or I can say it is dependent on beta 1. So hence, it is not a linear regression model. Fine. Yeah. So next one. So the next question, y equals to beta naught plus e to the power beta 1 x plus epsilon. Now let's see. Let's see whether it is a linear regression model or not. So del beta naught to del beta naught, if I differentiate it, so it is 1, no problem. With respect to beta 1, if I differentiate it, so it is 0 for this. And this is e to the power x. And with respect to beta 1, I want to differentiate. So if I differentiate, so it is kind of a e to the power ax thing. So e to the power differentiation of e to the power ax is a into e to the power x. So if I'm differentiating with respect to x, so here I'm with respect to beta 1. Okay, so it will be like x e to the power beta 1 x. Okay, so this is dependent on, which implies hence it is not a linear regression model. Okay, now I've done four questions. Now you just do the next one, the fifth one. Y is equals to plus log beta 1 x plus epsilon. What about this model? So whether it is a linear regression model or not. Okay, so let me try. So it is like dy over d del beta naught. So here you can say it is beta naught only here, so it will be 1. Otherwise it will be 0, so it is fine. Now del y over del beta 1. So it is log of, so here it will be 0 with respect to beta 1 if I do this. So it is d beta 1 of log beta 1x. So it is the derivative log x is 1 upon x. So it is upon beta 1 x oh, so if I consider d dx of log of ax, so what it will be 1 ax and derivative of a, so that is a here, so it will be 1 upon x, fine. And here it is derivative of log of beta 1x. So it is 1 upon beta 1x, and we are doing the derivative with respect to beta 1. So it will be x here when we again differentiate the beta 1x. So here it will be x. So it is 1 upon beta 1. Fine. So it is all again dependent on beta 1. So hence it is fine. I hope this is clear. Fine. So we'll move forward. So this is the model which is given as y is equals to beta root beta 1 x plus epsilon. So let us check del y over del beta naught. So it is 1, and del y over del beta 1 here beta 1 to the power 1 by 2. So it is by 1 by 2 beta 1 to the power 1 by 2 minus 1 x. Fine. And this will be 1 by 2 beta 1 x. So again we can say, so this is dependent on beta 1. So it is dependent on beta 1. So hence it is not a linear regression model. Fine. Now in the next question, if you see, so if you find out del y over del beta naught, so it is 1, no doubt, because these are 0 and this is 1. Del y over del beta 1, if I want to find out, so it is with respect to beta 1, so it will be x to the power beta 2. Okay, we can directly, so now from here only, if I do not want to check even the derivative with respect to y, because here only to the power beta 2, which is dependent on the parameter. So it is dependent on beta 2. So now from here only I can say it is not a linear. So just don't go on the thing that if the power of parameter is 1, then I will say that this is a linear, and if not, then it is not linear. So here you can also see that the power of beta naught, the power of beta 1, the power of beta 2, the power is 1 for all of them. But they are in such a way that the derivatives are not becoming independent of the parameters. Okay, so I want the model to be, the model will be linear regression model if it is like a linear in parameters. Fine. So let us consider these last two questions. So here you can see that y is equals to 1 upon beta naught plus beta 1 x plus epsilon. Here also beta 1 are in single power. There is no square, nothing, no cube, no 4, no betas to the power 4. But let us consider the dy over d beta naught. So here you can see that it is in the format of 1 upon x. Now derivative of 1 upon square. So it is like 1 minus 1 upon beta naught plus beta 1 x whole square. And again we want to find out the derivative derivative of this with respect to beta naught. So that will be 1. It is like this only. So this is dependent on beta 1 and beta naught, both. So dependent on beta naught and beta 1. Fine. So this is not linear, not a linear regression model. Fine. Now consider the third, this ith one. So it is y is equals to beta naught plus beta 1 x plus beta 2 x b3 plus epsilon. Okay. So del y over del beta, no problem, no, because it is 1. Del y over del beta 1, so it is x, there is no problem. Now del y over del beta, so it will be 0 for this, 0 for this, but here it will be x into beta 3. So which is dependent on beta 3. Fine. So it is also not a linear regression model. Fine. So this way you can, I have taken many questions on this. So I think this concept is clear, that how we say that whether a model is a linear regression model or not a linear regression model. Fine. Okay. So if there is some doubt regarding this question, then you may ask. You may ask.
Hello, ma'am. Ma'am, actually, you are not audible.
Okay, I'm so sorry. Actually, I was on mute and I explained the things. Okay, thank you for informing me. So let me start it again. So this question I
Sure.
was doing. This forfeited model basically y is equals to 4 plus x. So it is asked that what is the rate of change in average value of y. So what is average value of y? If I consider expected value of y, so that is equals to 5x only, because 4 is fixed constant, 5 is fixed constant, x is also in the particular setup where it is considered as a fixed. Okay. So in that case, the rate of change in average value of y will be expected value of y divided d dx of this expected value of y. Okay, because I want the rate of change in average value of y basically with respect to x only. Fine. So that is equals to 5. So basically 5 is the rate of change in average value of y. I can say with respect to x. Okay. So with respect to x, this 5 is the rate of change. Fine. If this were minus 5, okay, so basically what is the rate of change? So if I increase x by 1 unit, then the y will be increased by 5 units. If it was minus 5, then I can say that if I increase x by 1 unit, the average value of y will be decreased by 1 unit. Fine. In the same way, if I consider this second part, so for a fitted model, y is equals to 10 minus 3x, it is asked that what is the change in average value of y when x increases by 1 unit. So first of all, let me consider what is the rate of change basically. So expected value of y is 10 minus 3x, because x is considered as fixed in this setup. So the rate of change of expected value of y with respect to x is, with respect to x, if I differentiate it, it will be minus 3. So minus 3 is the rate of change in average value of y with respect to x. Fine. So now, if so here in the question it is asked that if x increases by 1 unit, what happens with the average value of y? Because the rate of change is minus 3. Fine. So I'm saying that if x is increased by 1 unit, then the average value of y, this average value of y is will be decreased by 3. Yes. Here 3 is in negative sign. So the average value of y will be decreased by 3 units if I increase x by 1 unit. Fine. So this was it. So I think this question is clear. Okay. So just tell me if there is some doubt in this question. If there is some doubt,
Ma'am,
then
can
we
you
can.
explain it again?
So this B part.
Yes, ma'am.
Okay. So basically here I'm saying that this is basically the fitted model y is equals to 10 minus 3x. Now it is asked that what is the change in average value of y when I increase x by 10 unit. So coming to this question, I'm just trying to tell that what is the rate of change in the average value of y with respect to x. So in order to calculate the rate of change, basically the expected value of y came out to be 10 minus 3x only, and the rate of change in the expected value of y with respect to x will be the differentiation of this with respect to x, so that is minus 3. Okay, now what basically it is interpreting, that if x is increased by 1 unit, okay, then the average value will be decreased by 3 units. Why? Because it is in negative sign. If it was positive, then I can say that if x is increased by 1 unit, then the average value of y will be increased by 3 units. But because it is here negative, so that's why it is saying that the average value of y will be decreased by 3 units. Okay. So I hope now it's
Yes, ma'am, got it. Yeah, yeah, got it, ma'am. Thank you.
okay. So then we'll move for the next question. Just see this question. So basically what it is asking, that a model uh, uh, okay. So he actually a fitted model in a data is y is equals to 12 minus 3x. Okay, so a fitted model is given by y is equals to 12 minus 13x, sorry. Fine. Of the pair of observation using the fitting is x is equals to 3. Used for fitting is x is equals to 3 and y is equals to minus 17. So one of the observation is 3. So one of the x for some I it is 3 and yi is minus 17. Right? I don't know which I, but for some I. So these are the observed values. Fine. So basically we have collected these values. Calculate the residual correspond. I want to calculate y hat for x is equals to 3. Fine. So for when xi was basically calculate the yi hat for xi to be 3. Fine. So when xi is 3, yi hat is what is yi hat? Value. So I know the fitted model. This is the fitted model. So what will be the value of yi hat? So yi hat will be 12 minus 13 into 3. 3x to be 3 calculate. So that is 12 minus 39. Okay. So what? Minus 27. Okay. So now I know the yi, I know the yi hat. So what is the residual? So residual is yi minus yi hat. So that is minus 17 minus minus 27. So it is 10. 17 plus 27. Okay, so it will be 10. Fine. So basically we have calculated the fitted value of yi corresponding to xi to be 3. And we know that what is the observation of yi, that is minus 17. And finally we are calculating the difference yi minus yi hat, which is basically the residual and which is coming out to be okay. So yeah, that this is a little kind of easy question. So I hope this is clear to you. Okay, so if this is fine, then so just see the data. So here, consider the following observation for dependent variable y and independent variable. Here, x is an independent variable and y is dependent variable, and the observations are given as in this table. So x is like 1, 2, 3, 12, 10, 8, 7, 5. So here you can see that when x is increasing, the y is decreasing. So we may get the from looking at the data, we can see that the relationship is kind of a in reverse direction. So when I increase the value of x, the independent variable, the value of the dependent variable is decreasing. So there is intuition called there is a kind of intuition that the line may be in a way like in a the slope is kind of a negative direction, like in a this way. By this, because as we increase this x, the y as we increase this y is decreasing. Fine. So this is the data first of all. Now the question is here that give the equation of line. So here I should write give equation of line, that is we are the linear regression, to be fitted in the given data using the method estimation. Okay, so I want to give the equation of the line basically. So for that, I have to estimate the parameters, the coefficients, fine, based on the data, based on the least square method which we have calculated the estimates, and those estimates are the function of the values from the data. Okay, so let us do this first of all. So we have, let me consider, this is uh, x, this is y. So x is like 1, 2, 3, 4, 5, 6, and 7. This is 13. This is 12. This is 10. 8, 7, 5, 3. Fine. Let me write the formulas here. So actually, if I write y equals to, so if I want to fit this line, so this will be beta naught hat plus hat into x. Fine. So now here, so this will be my line, the fitted line. Is what? So from the formulas, what is the beta naught hat? It is y bar minus beta 1 hat x bar. So it is y bar minus 1 hat x bar. And what is beta 1 hat? So it is syx sxx. And what is syx? It is summation xi minus x bar whole square. Okay, not whole square. It is summation xi minus x bar multiplied by y minus y bar. And sxx is summation xi minus x bar whole square. Fine. Syx on sx. I hope this is, yeah, it is the same. Fine. So for this, I need x bar, I need y bar, and I need x bar and yi minus y bar. So here, first of all, let me. So this is x. So what will be x bar here? Plus 1, 3 plus 3, 6 plus 10 plus 5, 15 plus 6, 21 plus 7, 28. So it will be 28. So that is 28 divided by 7. And y bar is 30 plus, so if I sum it, so it is 5. So what will be the sum? Just tell me. X bar will be 4 and y 8.2 approximately. So if anyone calculated, then just uh, tell me that whether the value I have calculated and the whether I this so these are correct or not. Okay, so I'm also calculating that whether 5 plus 6 plus 7, that is 20 by 7. So yeah, that is fine. The first one, 13 plus 12 plus 10 plus 8 plus 1 plus 5 plus 3. So it is 58 divided by 7. So yeah, it is 8.285. So let me consider this 0.28 only. Fine. So here is so let me make it in a little upper so I can see the sum values also. Okay. Here I'm writing 1. So it is 1, 2, 3, 4, 5, 6, 7. 13, 12, 10, 13, 12, 10, 8, 7, 5, 3, 8, 7, 3. Fine. So here the summation xi came out to be, the sum came out to be, it was 28, 58 here. So x bar is 4 and y bar is 8.28. Fine. Now I want to calculate xi minus x bar. I want to calculate y minus y bar. Fine. And I want to calculate their product. So it is not stored actually. Let me do this. So x, y is 1, 2, 3, 4, 5, 6, 7, and 13, 12, 10. So it was 28, it was 58. Okay, so x bar and that I have written there only. So I want to calculate xi minus x bar. I want to calculate yi, y bar. I want to calculate their product. So xi minus x bar into yi minus y bar. Okay, and I want to calculate minus x bar. Fine. So it is xi minus x bar. So 28 minus 1. So that is 27. No, not 27. So x bar is 4. Okay, so 1 minus 4, that is minus 3. 2 minus 4, that is minus 2. 3 minus 4, that is minus 1. 4 minus 4, 2. 5 minus 4, that is 1. 6 minus 4, that is 2. And 7 minus 4, that is 3. Yi minus yr 13. Okay, 13 minus 8.28. 8, so it is 4.72. 12 minus, so it is 3.72. Okay. And okay, so it is 12 minus, so it will be negative. Fine. So 8.28. So 13 minus 8.28. Okay, so it will be positive. So 13 minus 8.28, 12 minus 8 minus 8.28, 7.72, 8 minus 8.28. So there is 0.28 minus 7 minus 8.28. So that is minus 1.28. 5 minus, so it will be 3.28. Okay, 3.28. 0.28. Let's sum it. So the sum for this xi minus x bar will be 0. So that we do not want to actually. So do not want it. We want. So yeah. So 4.72 multiplied by 3. So this is minus of 14.16. Fine. This 3.72 multiplied by 2 minus 7.44. This will be minus 1.72. It will be 0. It is minus 1.28 and it is 3.28 multiplied by 2. 6.56, 5.28 multiplied 3. So this is minus 15. Squares also, so it will be 9, sorry. So 3 3s are 9, so it will be 4 here, 0 here, again 1 here, 4 here, 9 here. So if I sum it, so it will be twice the sum. 1, 10 and 4, and this will be 28. Okay. And I want to sum this also. 14 point, so these all are negative. Okay. So 14.16, 14.16 plus 7.44 plus 1.72 plus 1.28 plus 6.58 plus 15.84 is 40.02. Okay, so I'll write it here only. So here, summation xi minus x bar just give it is not saved. Okay, so just leave it. I have calculated the value, so I will just write it here only. That summation xi minus y bar. So that is coming out to be 47.02. And summation xi minus x bar whole square was coming out to be 28. We need it. Y bar we know everything again, other things we know. Beta 1. So beta 1 hat is syx divided by sxx. So that is just divided by this. That is 47.02 divided by 28. This is negative actually. Okay. So this is divided by 28. So it came out to be 1.6792. Fine. And beta naught hat is what? So it is y bar minus beta 1 hat bar. And y bar is what? 8.28. 0.28 minus 1.6792 divided by x bar is 4. So this is what? So this quantity multiplied by 4. So this came out to be 6.717 added by 8.28. So this came out to be 14.991. Fine. So our line will be y is equals to 14.99. This may be approximately 15 minus 1.8. So it is in minus. So you can see here the slope is coming out. It seems in a reverse direction, 1.6792 into x. So this is our fitted line. Fine. So this I will just update it in the slides. Fine. So this is the equation of the line. So we have plotted it. Find the values of y for x is equals to 5. Now I can see, again, I want to find out the fitted value of y. So for x is equals to 3, what is y hat? So basically I want to find out for x is equals to 3. Yeah. So what is y hat? What is y hat? So that is 14.99 minus 1.6792 multiplied by 3. If I find out that, so this quantity minus, let me write it again, 1.679 multiplied by 3 is 5.03. So it is 14.99 minus 5.03. So it is 9.95 approximately. Now for x is equals to what? Next one. So for x is 5, I want fitted value. So y hat is nothing but 5 here. So it will be, let me, so it is 1.692 into 3. This, not 3 actually, 5. 8.6 minus 14.99. So it is 6.594. So we have used 5 just in place of 3. So it is coming out to be this. So increasing the value of the line, or the value of the fitted value is basically decreased. You can see from here also. Okay. Now what is the next question? So find what is the sum of residuals. So residuals is yi hat. So residual is what? Yi minus yi hat. So these are the residuals, and I want the sum of the residuals. Okay. So we can find out by using, so for each, so these are the observed value, I know them. I can calculate the yi hat for each of the I, and I just sum it. Okay, so that calculation you just do it yourself, because that will be a very lengthy calculation. So each observed value will be this one, these are the observed value. Now for each xi, just calculate the values of yi from this line, okay, and just subtract from, like, from y1 yi hat, find the difference, yi minus y hat, and then again find another difference, and just sum all of them. Fine. So this was about this question. Now if we, so here we have just done all the calculation. Okay, what was so I just wanted to show you that how basically the things are working. Okay, so how basically the we will do all the calculation. But if use of R, then these all the things will be very easy. So here in this question it is asked that answer all the questions in question 4. So whatever the question, just answer them using R. Okay, so I will just show everything, the things which we have discussed here in R, first of all. Data. So let me first share the whole screen. Just wait a minute. Okay, so I have stored this data in x5 and y5 random data vector. So you can see it here. So x5 is this and y5 is this. Fine. Now, if I want to I want to find out the coefficients of the line, then I just do lm y5 tilde x5. So just see here, the intercept came out to be 15, and the coefficient, that is the coefficient of, or I can say the slope term, is minus 1.679. Whereas you can also see that whenever we calculate it, so the slope value is also coming out to be 1.6792. However, the intercept term is 14.99, and which is approximately same, 15.00 here 14.9, approximately same. So here also we are getting the same equation, but in a different format. So basically it is coming like coefficient and this, and you have to find out that what is the equation basically. Okay, now further it asked the fitted values. Okay, find the fitted value. So if by using R, we can find out directly the fitted values for all the xi's. Okay, so if I run this fitted dot values, and inside the parenthesis lm y5 tilde x5, if I run it, so you just see that for x is equals to 1, it is 13.32. For x is equals to 2, it is 11.64. And for x is equals to 3, we have calculated 9.96. So here also we have calculated 9.95. So which this is basically, we are not considering very many points after the decimal. That's why there is a slight difference. So it is 9.95, and here it is 9.9642, whatever. Okay, and further for x is equals to 4, it is given the fitted values for x is equals to 5, and for x is equals to 6 also 4.92, and we have, so there is a kind of error here, I think. Okay, so for x is equals to 5, it is 6.607, and it is 6.594. So it is, so there is 0.01 kind of error. So that is happening because of I've taken the decimal point. After decimal, I've taken 2 or 3 or 4 values, not more than. Okay, so the values are exactly same, and for x is equals to 6 and x is equals to 7 also. Now this is about the fitted values. Now if I want to find out now further, here in the question it is asked that what is the sum of the residuals. So residuals will be what? First of all, so residuals will be this value minus the observed value. So whatever the observed value, that is 13. So the difference of these value will be the residual for each xi. And if I want to find out the sum, then I will sum them up. So if I want to find out only the residuals, so here I will just run the command residuals lm y5 tilde x5. So this will give me the residual for each xi. So for x is equals to 1, it is giving me residual 0.32. For x is equals to 2, it is giving me 0.35. For x is equals to 3, it is 0.035. So this is basically very, like, it is around 0 only. Fine. And if I want to sum of all the residuals, then if I write the sum function inside it, I will write the residual, and here I am getting the sum. So the sum of the residual. So this is very low. The sum of the residual, it is very low. It is like minus 5.55 into 10 to the power minus 17. So it is very low. Directly, it is very near to 0. Fine. Further, in order to picturize the thing, let me show that what is the graph of these two, like what is the scatter plot for these. So if I write pi y5, then I will get this scatter plot. So you can see here that the data is like the slope of the data is having a, like, the slope is in the negative line, or I can say that the line is the slope of the line is negative. So basically, which means that when I'm increasing the x, my y is decreasing. Fine. Here if I see, then if I want to plot a line, okay, by some like random method, by hit and trial method. So here I have used this command ab line. A is equals to 15, b is equals to minus 1.7. So here basically the a is equals to 15 is the intercept term, and b is equals to minus 1.7 is the slope term. So here I'm just doing it manually, basically by hit and trial. I from somewhere I'm by seeing this data, from somewhere I'm hitting and trialing the things, that which slope and which intercept will fit this data. So if I run this, so you can see that here I got this line actually, which is going. So if I would have taken another a and another b, for example. Okay, if I take another A and another B, like for example, A to be 16 and B to be, for example, 1.9. Okay, then see this is a different curve. I mean, a straight line I'm getting. Okay, but who will ensure that this is the exact fit? So because here I am just doing the hitting trial method. Okay, so if I want to do that, so I'll just use this lm y5 x5. So ab line lm y5 x y okay, y5 x5, I should write y5 x5. Okay, and color to be blue, and if I fit it, so here you can say that okay, this is the best fit. This blue line is the best fit, because here we are using some statistical method. We are not doing the hit and trial method. We are using some of the statistical method in order to find out the best fit. Okay, so this is the thing. So this was about the how to picturize, visualize, and all those things in R. Fine. So this was it about this question. Let me consider the next question then. So let me write it here. See the R script. Fine. Okay, so the next question is, again I'm taking the same kind of a data, not the data, same kind of a question is it, but the data is having a different kind of a trend. Okay, so here the data is like the x is 2, 4, 6, 8, 10, 12, 14. So basically when x is increasing, the values of y are 5, 9, 12, 15, 18, 21, 25. So basically the values of y are also increasing. Okay, so now here we are assuming that there is a linear trend, or we can also see it by using the having the scatter plot, that what is the trend of the data. So let me, if I want to show, if I will show, so here see x5 and y7, if this is the value I'm storing. Okay, and if I want to plot these two datas, so you can see that, yeah, so there is kind of a linear trend in the data. Okay, by using the scatter plot you can find out, okay, there is a linear trend in the data. Fine. So in the question it is asked that give the equation of the line which is to be fitted in the given data using the method of least square estimation. The same thing which we have done for the previous one, we have to do for this also. Okay, further for x is equals to 9 and x is equals to 27, 21. Okay, so this I have written it wrong. So for x is equals to not 9, for x is equals to 4, and x is equals to 8. Yeah, or 12. Yeah. I want to find out the fitted values and what is the sum of the residuals basically. So the similar questions are there, but only the data is different. So what we will be doing, we will be again be calculating the mean of the data x bar, y bar, xi minus x bar, yi minus y bar, their product, and the xi minus x bar whole square, and we'll sum them up, find out the slope term, we'll find out the intercept term, then we will be able to find out the line. Okay, so I'll just do it in a like I will just do it in do a little of it. So it is like xy, so there is 2, 4, 6, so it is 2, 4, 6, 8, 10, 12, 14, 10, 12, 14 in a similar way, otherwise you can do it. Okay, 5, 9, 12, 15, 18, 21, 25. So what is the sum for it? So it is uh, the sum is 56 and 56 and x bar is 8. Okay. And 5 plus 9 plus 12 plus 15, 18, 21, 25. It is 105 divided by 7. So y bar is 15. Okay, so xi minus x bar is what? 8 is it there? So 2 minus 8 it is minus 6. 4 minus 8 minus 4. 6 minus 6 will be 0. It will be 2. Oh, so sorry. So it is 8 actually. So it is 6 minus 8 will be minus 2. It will be 0. It will be 2. It is 4. 6. It is 2. Okay. And 12 it is 4. Okay. And it is 6 here. Y minus y bar will be 5 minus 15, that is minus 10. 9 minus 15, so 9 minus 15 will be 6 minus 6. 12 minus 15, which is minus 3. 15 minus 15 will be 0. 18 minus 15, so it is 3. 21 minus 15, so it will be 6. 25 minus 15 will be 10. So what is the product? It is 60 here, 24 here, 6 here, 0 here, 6 here, 24 here, 60 here. What is this square? 36, 20, 16, 4, 0, 4, 16, 36. Now, I want the sum. So it is 60 plus 24 plus 6 multiplied by 2. So it is 180. Okay. So 36 plus 16 plus 4. 1, 1, 2. Okay. So I want the slope now. The beta 1 hat. So that is nothing but SXY. So this is 180 and SXX. There is 112. So this is 180 divided by 112. Okay, so it is 180 divided by 112. It is coming out to 1.607. And beta naught hat is what? Y bar minus beta 1 hat x bar. Y bar minus beta 1 hat x bar. So what is y bar? So it is 15 into x bar. So it is 8. Okay. So this is 2.1428. So our line will be y is equals to 2.1428 plus 1.607 into x. Okay, so let us do this using r also and see the things. So that will be given by lm x7 y7. So yeah, it is 2.143. So 1428 we were getting, and beta naught hat is 1.607. So yeah, it is coming out to be same. Find. And further what we want the fitted value of y for x is equals to 4 and x is equals to 12. So for x is equals to 4, for x is equals to 4, what is the fitted value of y hat will be what? So for x is equals to 4, it is 2.1481428 plus this is 4 here, so 1.607 into 4 here. So what will be? It will be 1.607 into 4 plus 2.1428. Yeah, so it is 8.5708 for x to be 4 and other x to be 12. So if x is 12, y hat is 2.1428 plus this 1.607 into 12. So 1.607 into 12 plus 2.1428. It is 21.4268. Okay. So let us do this fitted values with respect to r also. So here you can see these are the values. So for y x to be 4, it is coming out to be 15. So we are getting, okay, wait a minute. It is coming out to be 15 here, and for x is equals to, Okay, so basically it is giving the value for x, the fitted value it is giving for 1, 2, 3, 4, 5, 6, 7 actually. But okay, so 1 and 2. Okay, okay, fine. So this is 1, 2, 3, 4, 5, 6, 7. That means that is the first value of x1. This is the second value of x1. This is third value of x vector, and this is fourth value. So basically the second value will be the 4. So this will be the corresponding value. So that is 8.57. So yeah, that is correct. And the 12 is the last second value. So it is 21.428. So yeah, it is also correct. So yeah, so there was a confusion. So I was thinking that it is like 4 here, and as corresponding 4 it is coming like 15. So it is not corresponding x is equals to 4, it is corresponding x is equals to 8, but the fourth value of x7, right? Okay. So this was about it. So I have shown the what is the sum of the residuals. So sum of the residuals you can get it from this command sum residual. So that is coming out to be very low. So it is very near to 0. Fine, so this you can get, and also you can see here this is the plot. So this is the plot, the scatter plot of the data and the fitted line. Okay, so here you can see the trend is like the slope is positive. Okay, so this was about the question number 6, and in question 7 also I have written that you have to do all the things in using R. So here also you can see the R script. Okay. Fine. So this was about these two questions, where in one question we have discussed the trend of the data was linear, but it was in a negative direction. The slope was negative, and here the trend of the data is also linear, but the slope is positive. Fine. So we have discussed these two questions theoretically as well as in a application sense, like how to use in R, how to use R in order to do the things, the application of R, I can say. Fine, so this was it about the today's lecture. So the recording for the today's session, I will be uploading it on YouTube. You may access it from there, and the PowerPoint presentation and the R script will be added to the Google Drive. Okay, and the last day to submit the assignment 9 is on 25th of March. So just submit it if you have not submitted it. And the next session for the week 10 lectures will be, the live session for week 10 lectures will be on 30th of March from 6 to 8 p.m. Okay. So now if you have any doubt or something like this, then you may ask. Okay, otherwise we will end this meeting. Okay, so any doubts, anything? Any doubt? So anything regarding the questions, anything regarding the theoretical sense, or in a like how whatever the things we are doing in art, anything regarding that? If not, then we will be ending this meeting. Okay, so if there is no doubt, then we'll end this session. And thank you for joining. Thank you for your patience. And also, I want to let you know that we will be having the next session on 30th of March. So let's meet then at that time. And till then, thanks for joining. Okay.
Thank you, ma'am.
Okay. Thank you. Okay, then we'll be ending the meeting. So let me just stop the recording.